Any questions, discussions related to this morning? Maybe we should start with that. Things you're not happy about, disagree, or like. Really?
Happy enough.
Okay.
Would it be possible to have your slides available?
Oh, of course. Yeah. I plan to do that. Actually, I should have done that earlier, but it's always a question. Is it better to do it earlier, distract you, or just have your full attention here and then you can look at it later? Okay. All right. So I would like now to talk about upscaling porous media, and I will start with what I call single-phase flow. So that means that the solid structure, the porous medium are filled with one phase only, and this is a single phase, single component phase. And then see how later on we go to multi-phase. To do the upscaling, you really have three options. One is to write the governing equations of flow. By governing equations, I mean Navier-Stokes equation, elasticity equations. You can write them at the scale of pores and grains, and then define an REV and average them over REV. That's one option. The other option is that you can write only the conservation equations at the pore scale. So by now you know that we have a set of conservation laws that are valid universally, and then we add to them constitutive equations. So the first one is you take the final product and average. This one, you just average the conservation equations, do not involve any constitutive equations, and then develop the constitutive equation at the macro scale. And that you can do again either in an empirical fashion or do it the way we did this morning, following a procedure. And finally is that we start at the molecular scale, as we did from the very beginning of the course. So here is at the pore scale and grain scale. This is at the molecular scale. And then go to, and then average the conservation laws from molecular scale to the Darcy scale, and then develop constitutive equations. You see the difference between the three? Okay. This first one, I'm not a fan of it. So the reason is, this is what originally, the first upscaling of equations of flow were done this way. They took Navier-Stokes equation, averaged it. The problem is, as you saw, there are already a lot of assumptions put into Navier-Stokes equation to get it. And I ask myself, if I have a porous medium and I want to study flow of a liquid in there, why do I have to start with all those assumptions? What if the fluid doesn't behave like Stokesian flow? What should I do then? We can go back to these equations and write them for non-Stokesian. Okay, that's true. But it's already you are putting in assumptions there that linearity and so forth, that at the macro scale, we don't know how good they are. There is another problem is that, I don't know, has anyone followed the work of Jacob Baer or Steve Whittaker for averaging? No. If you do that, when you integrate those pore-scale equations and go to larger scale, you get a lot of, you have the second derivative of velocity, the Laplacian of velocity, you have all kinds of product terms. When you take the average, you get a lot of extra terms. You don't know what they are. Do you know what they do? They make appropriate assumptions to show that they are, or to assume that they are negligible. You throw them away. And in fact, you make appropriate assumptions in order to get Darcy's law. So it's not the way I like it. I like to be able to follow a procedure, obtain results that I don't know I have to get those results. So I'm not a fan of that. And these are already, as I said. There is an advantage, I must say. We get a direct link between macroscale coefficients and microscale parameters. That's nice.
May I ask,
Sure.
is this what is called the TCAT procedure?
So TCAT is basically the rational thermodynamics approach I explained today. The major difference is equations of thermodynamics, like Gibbs relationships, Clausius Duhem relationships, they are also averaged. They are written at the pore-scale and averaged.
Yeah.
As you noticed, for example, for fluids, when we start with developing the constitutive equations, there is no pressure. We only have stress tensor. It comes out naturally. And in fact, there are some complex systems that the pressure is not simply dA0. It could be other things involved. So what is pressure itself at the pore-scale? I don't have to specify. But they start with the pressure at the pore-scale already, and they write all the equations of thermodynamics and average those, as well as all this rational thermodynamics. Most of the time we get the same results as we get here. Okay. Then the option 2, which is to really work with the conservation laws only, either derive them from molecular scale or pore-scale, and develop constitutive equation at the macro scale. And this is what I like, because in fact, that's the approach I follow to get Navier-Stokes equation or all these other relationships at the pore-scale. So I say, yeah, I follow that for the porous media. It just follow the same procedure. The advantages are that we develop the constitutive equation at the scale of observations, because there was this discussion yesterday. At the porous scale, water is viscous. But at the Darcy scale, actually we treat water as non-viscous at the macro scale. So I make observations at the macro scale, at the Darcy scale, and then say, okay, let's use those observations to develop constitutive equations. Then all simplifications have a clear physical meaning, so it's not, I don't have to make appropriate assumptions, throw away terms, I don't know what they are. And the disadvantage is we don't get a direct link between macro scale coefficient and micro scale parameters.
And a question about pore-scale conservation equation. Like take momentum, right? The pore-scale momentum conservation, if it is conserved actually. So what do you mean this pore-scale momentum conservation?
Okay, I'm going to actually show it in a minute.
Okay, yes.
Yes, that's a good question. So I'm going to start today not from molecular scale. I want to average the pore scale conservation laws. And we need to define average quantities. And I have certain criteria for defining average quantities. Actually, I already used these criteria when I went from molecular scale to continuum scale. We define an average in accordance with the measurement. I gave the example of velocity. The velocity we measure often in porous media or in many other applications, in river, or it is a momentum that we measure. It's the total momentum that we measure, and then we basically divide that by mass, we get average velocity. So that's one criteria, and there are other examples that we come to it later. We have to have conservation of entities between subscale and macroscale. If you recall yesterday, we said, for example, at the subscale, we define, at the molecular scale, we define momentum to be mass times velocity. So if you have a large number of particles, you sum all the mass times velocity, that's total momentum. Now I go to macro scale, I have mass density and I have a velocity. So what is momentum? Mass density times velocity. So mass density times velocity must be equal to the sum of all mv's. That's what I mean by this conservation. I have other examples that I will show you. Averaging must be adding up additive quantities. You cannot just average everything you want. For example, you find average temperature over a medium defined as the integral of temperature times volume. What is temperature times volume? It's not a physical quantity. You cannot add it up. So that's actually not a physically meaningful. Statistically, it's meaningful, but it's not a physically meaningful quantity. Or velocity times volume. I integrate that. What is velocity times volume? It's not a physical quantity. You cannot integrate that. You cannot add it. It must be additive. Rho v dv, that is additive because rho times velocity is momentum per unit volume times volume, that's momentum. Add all the momentums, you get total momentum. And then divide by the total mass, you get the average velocity. Yesterday we went through this, or the day before, from molecular scale to larger scale, yesterday. And there we define things like a stress tensor and the heat vector in terms of molecular quantities. We really should follow the same sort of definition. That's what the fourth one is. So we'll see how these apply here. So this is the mass balance at the pore scale. If you are inside a pore, a point within the pore, now that's a continuum. It's like, it could be inside the pore, could be inside a lake, could be inside a river. At any point, you have a mass conservation. And then you can run momentum conservation at any point.
And what about the surface between the rock and the fluid?
That's a boundary condition. When you solve the Navier-Stokes equations in a pore, the solid boundary is a boundary condition.
Yeah, but I mean, if you take the dividing surface of the rock, you have an excess density of the fluid at the surface. So
That's correct.
Is that in that equation?
No, because this is a point within the fluid.
Oh, okay.
So I have, you remember the molecular picture? In this porous space, I have zillions of molecules. I take a mathematical point and I put my psi there, and then average for that point in the fluid, in the pore, I have a mass density.
Yeah, but so then you have a conservation equation of mass inside the pore.
That is correct.
But you do not describe the possibility that mass is stored extra at the surface, or that it is depleted.
Yeah, but that's the boundary of my pore.
So that
my world is this. This is my world. That's my domain.
Sure.
In this domain, the fluid lives. If I take a point here,
the fluid lives. That's a matter of definition, right? I mean, if you take the equimolar surface of the solid, part of that fluid of you is living on the surface.
yeah, but not the one which is in the middle of the pore.
Sure, but if you then look at the change of the density, and you go to a region where more of the particles are absorbed on the surface, you don't describe that.
Yeah, but then at the surface, I need another mass balance equation.
Okay. So
At the solid water interface, you have another mass balance equation.
sure. Okay.
This is not for the solid water interface. Okay, so that's inside the pore. So let's take.
Inside the pore, I understand.
Okay, now that's what I mean. Yeah. Now I must say, for this single phase flow, I'm not going to treat the solid fluid boundary as a separate entity. If you wish, I say all the molecules that belong to the solid-water interface, I count them as part of the solid. It's a simplification, and I can always, actually, you will see that when I go to two-phase flow, then I put all those interfaces there. And I could do that here, but let's not do that here. Okay, so let's say you are doing Hagen-Poiseuille flow. Okay, what do we do? For Hagen-Poiseuille, we have a pore, it has boundaries. Inside the pore, at every point, you write the mass balance, momentum balance, you integrate it. Once you integrate it, you need the boundary conditions. Okay. So at this stage, inside the pore, I have a balance of mass. This, and then, actually, sorry, I write this not only for pore, I write it for inside the grains as well. So I write it everywhere. As the interface, potentially I should write something different, but let's not do that for now. And then we average this over the volume of the fluid separately, the volume of solid separately, because those are different materials. So if you do that, I integrate over volume of V alpha, where alpha is either fluid or solid. We note that potentially this volume is a function of time, because the solid could be deforming. And so I just integrate this. Now, then for these, like yesterday, we needed to switch the order of integration and summation, the derivative and summation. Here we want to exchange this order, because the integral of rho dV, that's my average mass density. And I want time derivative of average mass density. So I want to exchange this. I want to exchange this order. But because this is a function of time and also a function of space, I cannot do that simply. So that's the same thing written in shorthand notation. And then, let me remove that. Okay. Now, I define average mass density to be the sum of all masses within that volume V alpha. By the way, this V alpha is my representative elementary volume. Is not the whole porous medium. It's only, remember that block definition of psi, that's what I'm doing here. I have an REV, and within that REV, I sum up all the masses divided by the volume. Now, that's my average mass density. I also define an average velocity, which, as you can see here, is defined through the momentum. So the total momentum divided by total mass is the average velocity. Now then I have what is called time averaging theorem, which allows me to exchange this order for any function f. I can write this, and now this is a sort of transport theorem basically, where A alpha beta is the boundary of V alpha. In single phase flow, the boundary of the fluid phase is a solid fluid phase, and the boundary of solid phase is also fluid solid phase. This boundary. So there's only one boundary. W is the velocity of the boundary. I guess you're all familiar with this. Anyway, this can be proven. Some of the early literature on averaging upscaling porous media was to derive this, but hopefully it's an identity from transport theorems. And then the spatial averaging theorem allows you to put the del dot outside, and then this is like divergence theorem basically. And then you have rho v dot n dA over A alpha beta. Okay? So if I put this in here, substitute that, substitute this in here, I get this is my time rate of change of velocity, because this d rho dt based on this definition is rho alpha v alpha. So that's that term, that's that term, and I put those two terms together, I get this extra term. Okay, now v alpha itself is a function of time and space. I don't want that, so I divide all of this by the volume of the porous REV, and the volume of REV is constant. I use the same REV everywhere. So if I do that, then I get V alpha over V, which we call porosity. volume fraction. So epsilon alpha is the volume fraction of the alpha phase. In case of fluid or pores, we call it porosity, and for solid is 1 minus porosity. Okay, so if you put now that in there, this term here, this is really the exchange of mass between solid and fluid. And that's where the boundary comes in terms of the interaction between the two phases. And we denote that by exchange of mass between alpha and beta phases. So, and that exchange must be, of course, sum of it 0, because what goes to the solid is equal to what leaves to the fluid. And so that is the mass balance equation at the macro scale. Is that clear? You're not 100% happy? You're still contemplating it?
Yeah, just thinking.
Yes? I'll be happy to explain.
Oh, that's fine.
Okay. So then we go to momentum equation. Inside the pores, we derive this equation from molecular approach yesterday. So we have this at every point within the pores or within the solid grains. And then again, we average that over each phase separately. Now we come the same sort of issues we got yesterday. The average of product of terms. This one is not too difficult because again we use time average theorem. Apply here. To that also apply spatial average theorem. So if we do that for time average theorem, I get the time derivative of this average of this, which is, we already define average velocity to be average of that, and then here epsilon alpha. For that, we get two terms because same as yesterday, we define a deviatoric velocity to be the local velocity minus the average velocity. And if we substitute for V alpha here, we get a product of average velocities, product of deviations average, and then deviation time average velocity, whose average is 0. So we only, from this, we get two terms, this term here and this term here. Now, from del dot T alpha, we get the divergence of epsilon alpha T alpha, and we get from the spatial averaging theorem a term related to the dot product of the stress tensor at the boundary between fluid and solid. The gravity term simply gives you G, assuming to be constant, is simply giving you the mass density times G. And from these two terms, I get, similar to the mass balance equation, a term which is exchange of momentum between the two phases. We should note that the exchange of momentum between two phases is only non-zero if there is a mass exchange between the two phases. Otherwise, this would be also 0. Okay, is that clear? So this is my macro scale momentum balance. Everything is macro scale. These are all average quantities. Now, this you can say is not average quantity, but I call it force exchange between the two phases, and I denote it with a symbol, then it becomes a macro scale. This is also macro scale, but this one is average of this subscale momentum transfers. Has anyone a suggestion what should I do with this term? Should I give a macro scale symbol to it, and that's also a kind of, because I don't want to have detailed video. I have to deal with this thing. See, it has the same, it's the same sort of animal as this. It is what is a stress tensor? It is contact, exchange of momentum as a result of contact without any macro scale flow occurring. This is exchange of momentum as a result of flow, because there is here flow, movement, then we have exchange of momentum. So if you have a imaginary surface, this term says there is a flux going through that imaginary surface, a flux of momentum. This one says this part exerts a force on that part, and that's momentum exchange. This one does the same. And it says that it exists even if the average velocity is 0. So you can imagine I have a porous medium where on the average there is no flow through the porous medium, but within the pores the water is moving back and forth. Now that's on there. And it's the same kind as this. So you could at this stage decide to say, and similar, this was actually the term yesterday we also had for molecules, and we said that is part of the stress. That was actually the pressure, if you recall. So we could put it part of this, but you could also leave it here. And what is interesting is that if you leave it here as it is, these two terms will always appear together. If we go through the entropy inequality procedure I presented today, if we go for this through it, you only get a relationship for the sum of the two. So it's really hard, they belong to each other, and that's what we call the macro scale stress tensor. And then this would be our macro scale momentum balance. The inertial terms, stress tensor divergence, gravity term, and the exchange of momentum between the two phases, and that exchange of momentum is partly because of contact forces, partly because of mass exchange. And that's this definition of macro scale stress tensor. And the sum of the exchange of momentums must be 0. So this is my macro scale, Darcy scale conservation of momentum. Simple. Okay. Now, if you're happy with that, then I can do the same for the energy balance. I don't know why I don't have it. You can do that, and you get basically, please note that these balance laws are very similar to the Porous scale balance law. It has the same form. These are now average quantities, with one exception: the right-hand side is not 0, because we have converted our just juxtaposed pore-solid picture to two continua that are overlying each other. They are intertwined, these two continua. At the Porous scale, at every mathematical point in the space, we had either fluid or solid. Here, at every mathematical point, we have fluid and solid. They are coexist. And that's why they also exchange with each other at every point a momentum or a mass or energy. So that's non-zero on the right-hand side. You cannot say, you can say, okay, the momentum is not conserved. Yeah, for one phase, indeed, you look at it, it's not conserved. But you can say also, yeah, I put this on the left-hand side and that's equal to 0, that's conservation too. It's anyway, there is an equality, and that's conservation. And definitely the sum is 0, so total momentum for the whole, the two phases is conserved. Now I get a similar equation for energy. I'm not sure why it's not here. Then I go to entropy. That's a little bit different and interesting, is that at the Porous scale and the grain scale, I have the momentum balance equation I had proposed yesterday at the first continuum scale. It's this one here, and where we said this morning we worked on it that because of the second law, rho gamma must be non-zero. This is once again an observational fact based on our experiences. Now we average this for the porous medium. So we average this over REV. If you average it, similar to the previous term, now this gives you this term here, plus due time average theorem and integral over the boundary with solid phase. This one gives you this term here with an integral over the sound boundary. The sum of those is this exchange of entropy between fluid and solid. Now that gives you also the macro scale and so forth. And the right-hand side gives you this net rate of production of entropy for the alpha phase. Now then you can say, you can also average this, and therefore you get that this must be non-zero for each phase separately. But that is not the observations. It would be like to say, look, if I have a refrigerator, and this refrigerator is separated from the outside world, then its entropy can only increase. But if you connect it to this outside world, it's possible that the refrigerator entropy goes down, but outside world entropy goes up, and the sum will still be non-negative. So when you have interacting media, it is not necessary for each of them to observe the second law of thermodynamics. This is also an experimental observation. So what we then say here, we cannot impose this when we go to the larger scale. At the larger scale is the sum of the two entropy production rates that must be non-negative. In fact, we can do this as an exercise. Next week we have exercise. If you don't do this, if you assume each of these individually to be non-negative, you get all kinds of results that are say, yeah, but this is nonsense. So that already tells you that, once again, these are not laws of God. These are things we say based on observations that we have. Okay. Yeah, sometimes instead of going through these already prepared, in order to go slower, I write everything by hand, one by one. That takes longer, but this is repetition of what I have already presented, so I'm not going to go through it. So I have now derived balance laws at the REV scale, and I have a second law of thermodynamics at the REV scale. Is everyone happy? Is it okay? Any reservations? I'm not having any tricks anywhere, nothing hidden, okay?
But you are saying that gamma alpha can be negative.
That is correct.
Yeah.
Yes, can be negative, and the gamma beta must be more positive,
Yeah, sure.
to make the sum.
Can the beta phase be an interface?
Then I need to define interface. What do you mean interface with what? Because
Yeah, between the fluid and the solid.
yeah, it can
There
be,
is
but
an
then I
interface.
still have to add the solid here. If I want to model the interface, then I need to have three entities: fluid
Okay.
phase, solid phase, and the interface.
Because the surface tension doesn't exist alone.
That is correct. And in case of single phase through porous media, yeah, you can say what happens at the interface unless you have things like solutes and colloids, and then they interact with the interface. Otherwise, for single phase, single component liquid moving in porous medium, I say the interface, its main role is frictional,
Yeah.
provided friction. Even if it is dissolving, let's say, or we have precipitation, still it is not that important. But we can put it in. As I said, for two-phase flow, I put in the interfaces. Okay, then I would like to go to say, okay, how does the development of the considered equations works for porous media. Okay. Now, so if you have a porous medium, we had this picture this morning, then we say that, you see, one major difference between a fluid and a solid is that a solid, to give it a shape, you have to exert force on it, you have to change its free energy. It doesn't happen by itself. But the fluid can always take the shape of its container. It can flow and move without having to undergo thermodynamic changes. Its density, temperature, and pressure can remain the same while changing shape. So changing shape does not constitute any internal change of the fluid. But for the solid, there is. So, and because we have a porous medium, we say the solid has a shape, it occupies the space at time t equal to 0, and by motion it is taken to new position, new configuration at time bigger than 0, and there is a material coordinate xs, s stands for solid. There's a spatial coordinate that is occupied at time t, and this spatial coordinate is a function of the material coordinate of the solid phase. So we carry now here is the same as what we had this morning, except that we assign this superscript s. This is for motion of the solid. And this velocity of solid is the derivative of motion following a given material point. For the fluid, we don't have the concept of deformation, so we introduce the velocity field as given. Average macroscopic velocity field is given, is a function of x and time. We don't relate it to a deformation. Then the conservation laws, I just derived them. Maybe a little bit different notation here. This is the mass balance equation, exchange between fluid and solid. This is material time derivative written as a partial derivative plus v dot divergence of divergence, and then the sum of those must be 0. I also have these other balance laws for momentum, for energy, and the balance of entropy, where this must be, we say something about it from second law. These are all subjects to the fact that the sum of, oh, by the way, here I have written it for a non-reacting porous medium. And I want to look at single phase flow in non-reacting rigid porous medium. Now, being rigid or not doesn't affect my balance laws, but non-reacting affects it because now I have 0 here, and the exchange of momentum is only because of forces, there is no mass exchange. There's also an exchange of energy between the phases at the boundary, and exchange of entropy. The sum of the exchange of momentums must be 0. The sum of the exchange of energies must be 0 between the two phases. But the sum of exchange of momentum between the two phases doesn't have to be 0. It should be non-negative. Okay. I then introduced the same sort of conceiving relationships we had for a single phase material, define the production of entropies because of the production of energy or supply of energy. The flux of entropy is related to flux of heat, and we define Helmholtz free energy. If we do that, then for each phase we get this, but of course we shouldn't have, this was for each phase, we had it this morning. Now we get this for each phase, but then the sum of it must be non-negative. So that's what we now repeated here, and this is the sum. So this is now my entropy inequality. You see that similar to what we had this morning, You have a time derivative of free energy, entropy times time derivative of temperature. You have it twice for the fluid and for solid. Then you have a stress tensor multiplying the deformation rate tensor for fluid and for solid. Then you have the exchange of momentum between the two phases and multiplies the difference between velocity of the two phases. So I have used the notation here that this VFS is velocity of fluid minus velocity of the solid. Oh, sorry. No. We can do that. Okay? So that's the relative velocity of fluid to solid. Please remember, these are all macro scale, REV scale. Okay? And then the heat vector multiplying temperature gradient for solid, fluid, and solid. Is it? I hope it's familiar. We had it this morning, except that now we have it for the sum of them. Okay, so these are my balance laws and the second law of entropy, second law of thermodynamics. Then I go to the constitutive theory. The axiom of causality says that the thermodynamic phenomena are caused by motion of the solid, motion of the fluid. We could potentially have a velocity of the solid and density of the fluid, density of solid, and temperature of each of them as my independent variables. But axiom of objectivity says you cannot have dependence on velocities because these are not objective. They are depending on the observer. Their difference, however, is objective. So we can have a dependence on these only through their differences. Then this is objective because this is independent of the observer. Now, and then we still have these. And then...
And these quantities are defined in each point in the porous medium, both in the fluid and the solid.
Is the quantity defined at any mathematical point in a space, and that mathematical point contains solid and fluid. It's overlapping. It's a mixture theory.
So in each point in space, you have two temperatures.
Correct.
Okay.
That's correct. That is what is said here. You have two velocities, you have two densities, everything is...
Yeah, I understand the two velocities, but I mean, I observe that you have two temperatures.
That is correct. And whether in a certain set of thermodynamic conditions they are equal or not, yeah, that is possible. That they may be equal, but not always. They don't have to.
Can you give an example of that?
Yeah. For example, I can show you results of experiments where we do micromodel experiments in a micromodel where we inject two immiscible liquids, fluorine and water, into a micromodel. Using a camera, we can see where the fluids are. Using an infrared camera, we can see the temperatures. So we have the temperature felt in each solid, fluid, and each fluid. And if we average those temperature fells over an REV, so at any given point, we get two different temperatures, depending on how fast the flow is, how big the temperature difference was, of course. But that's very well possible. If you come in, if the residence fluid and solid are at temperature of 20 degrees, and you come in with 50 degree another liquid, it takes time before they reach the same temperature.
But these temperatures are separated in space.
No, I'm talking about not pore-scale. So
Yeah, pore-scale.
average
okay.
scale.
Yeah.
At the
okay.
pore-scale, at any point, I have either this fluid or that fluid,
Yeah. Okay.
or solid.
Okay.
Average.
Fine.
Yeah, I just want to know this saturated porous media, is that means a single phase or?
It's single phase. There's only one fluid.
Okay.
Yes, there are not two phases. because that becomes a lot more complex, and I wanted to do that.
So it's equal to single phase plus this just the one fluid and one matrix.
Correct. There's only one fluid and one solid. Yeah. Otherwise, I should have had a different index for F. There's only one fluid. Okay, and then, as I said, the axiom of objectivity says we should have this. And then, axiom of determinism says that these dependent variables, energies, entropies, stress, oh sorry, this must be S. Entropy, stresses, heat vectors, exchange of momentum between the two phases, exchange of mass and energy, they all depend on the independent variables, which are here. These are the independent variables. Now, as I said, axiom of objectivity requires that you depends on the difference of it. And here I have done what I did this morning. I say it depends on all points of the body, all past times. And if I then make a Taylor series expansion around the current point, I get the divergence of velocity of fluid and solid potentially. And if I use axiom of smooth memory, I expand over the current time, then I get the time derivative of temperature and density, and I also have porosity and porosity gradient and so forth. So these are potential independent variables. So if I now go to non-reactive rigid porous media, these are my, again, balance laws, and the Consteve equations are given here. So all these are functions of rho, temperature, rho of the fluid, temperature. Note, I don't have the motion of solid here anymore because it's non-rigid. It's rigid, non-reactive. And because it's rigid, porosity is not a function of time anymore, and the gradient of porosity is not a function of time anymore. And this is the velocity, relative velocity of fluid and solid. I make this extra assumption. I now assume the temperatures to be the same. I don't have to. If I don't do that, here I get some extra terms. But for now, this is we are known as local thermal equilibrium. At any given macroscopic point, the two phases have the same temperature. So if I do that, the entropy inequality now becomes this. I will introduce that earlier, except that now I don't have TF and TS. And if I expand the fact that A is a function of these quantities, then I get, yeah, this is the expanded form. I think I even have thrown away dependence of free energy on porosity and the gradient of porosity. I only kept the dependence of free energy on velocity differences and on density, and I do not have, yeah, that's right, okay? So if I look at this, I see that this term is appearing linearly. This term, no other term in here is a function of d theta dt. No other term here is a function of dv fs dt. I can put these together. I don't get into details, but then there would be a gradient of VFS that would be linear, so I leave it like that. No other term is a function of this. This I don't have to say anything about it because it's non-rigid, so this is identically zero. It's rigid, so identically zero. There is no deformation rate for the solid, so this you can throw away. That's it. The other terms are functions of VFS, the velocity difference, and function of temperature gradient. Or was it non-heat conducting? It's yeah, okay. So I don't know, I guess everyone was here this morning. This means that that coefficient must identically be 0. This must be identically 0. This must be identically 0. This and this must be non-zero, non-negative, this sum. So from there, I get a relationship between entropy of the two phases with their energies. Note that I do not get individual entropies being related to the change of Helmholtz free energy with temperature. The sum of I define this as they come together, they are, say, added to each other, so I call that, give that one, it was non-heat conducting. So that means I didn't have a dependence on temperature gradient, so that must be also 0. So if there is any heat, it's because of the fact that there is an imbalance of entropy with the time rate of change, the temperature change of the free energy. And then I find that the stress tensor of the fluid is equal to, is isotropic, and this PF is equal to rho F squared dAF d rho F. That comes out of here. You see? This must be 0, so the stress tensor is minus this. And this I identify as pressure. So now pressure comes in. This is macro scale pressure. How is this related to pressure inside the pores? This doesn't tell me. But it's pressure at the macro scale. It's defined here. There is a minus sign. Okay. So that is, and TSKL is not defined because a rigid solid can take any stress you want. It's not defined because it multiplies 0. And the residual entropy inequality becomes this. Is that clear? Yeah? So now I have a formula for my stress tensor. The only thing I now need actually, because if you recall momentum balance, one of the terms in the momentum balance was exchange of forces between fluid and solid. And I need that. Now from this I can get some information about it. And the information is as follows. I define equilibrium to be when the velocity differences between solid and fluid is 0. Basically there is no flow. That's equilibrium. Now, under equilibrium conditions, then the entropy inequality becomes 0. It's absolute minimum. So its derivative with respect to this variable that makes it minimum must be 0. That means this must be 0 at equilibrium. So the exchange force between fluid and solid at its equilibrium is equal to pressure times the gradient of porosity. So that means at non-equilibrium conditions, the exchange force is some equilibrium value, that's this one here, plus some non-equilibrium value, which still is a function of density, temperature, porosity gradient, and velocity difference. If I still have to say something, how does it depend? And that is your choice. What is your material? How does it behave? Now, often linear. Okay, if you make a linear expansion in terms of VFS and in terms of epsilon k, then we get nothing in epsilon k, only VFS. Then we get this as the linear relationship, and we can put this back into the entropy inequality, and we'll find that this RKL must be positive, semi-definite. This is the inverse of permeability, actually. So if you put that back, everything into the momentum balance equation, Remember, TKL is only pressure, porosity times pressure, and this is minus pressure times gradient of porosity plus a linear term in VFSL. That's this term here. We put that for this substitute here. Now, here there is a porosity times gradient times pressure that cancels this. This is a plus, that's a minus. So P times porosity gradient cancels that. It is only porosity times pressure gradient left from that term. Gravity is here, and then we have that term here. Now, if you neglect the the inertial terms, then we get Darcy's law, basically. So yesterday I was very sarcastic about how Darcy's law was developed or extended for non-isothermal, compressible fluid, three-dimensional, unsteady state, deformable solid. Actually, you can see that that was not too bad. You get it. This is valid. It's valid. Here it was rigid solid, but we make it deformable also in a minute. You'll see that it's still valid. So it's not too bad. For single phase flow, that is something that comes out of this procedure. And it's not too bad. As I mentioned yesterday, porosity is really put in here for the sake of scaling, because we know that from our experiences that this coefficient varies with the inverse of viscosity. So that's why viscosity is in here. But there was no viscosity in my conservation laws and in my considered equations. It was inviscid fluid. Okay? Yeah, I think I can stop here. Maybe I can quickly show that for a deformable porous medium, then you remember this morning I said that for a porous medium, if you know that for a solid material, if you know the deformation, you don't need to include density as an unknown, because density is known. Rho times determinant of deformation is equal to rho 0. You know initial value, you know deformation, you know rho. Now when you go porous medium, that's not the case, because in the porous medium, for the solid phase, it's epsilon times rho times Js that is equal to some initial value. And here, even if you know deformation, that is this Js, still you cannot say you know rho. You know epsilon times rho. So one of these must be included as an independent variable in the set of independent equation. And here I have decided to include rho s, but you could have included porosity. There's no difference. So compared to the previous set I showed you, now I have included the formation of the solid. So this is the strain tensor for the solid, and I have included also the temperature gradient. And so if you then go through the whole procedure, you will find that the solid free energy, almost free energy, is a function of its density and its deformation, and solid and temperature. The fluid is only a function of density and the temperature. The sum of the entropies must be related to the change of free energy of the whole medium with temperature. The stress tensor for fluid is only pressure, which is defined this way. For the solid, the stress tensor is partially a pressure from the fluid. Those of you who know Biot's theory, they say stress tensor of the solid, and there is argument for that, very well placed. But here we derive it. It comes out of the entropy inequality that solid stress tensor receives a contribution from the fluid pressure because they are intertwined, plus its own deformation. And this is what is called effective stress tensor of the solid. And the total stress in the medium is the pressure of the fluid, because then we add this to this epsilon s plus epsilon is 1, you only get minus pf, and that's effective stress tensor. And the equation, and this was proposed by the way by Terzavi. And the momentum exchange term takes this for, again, it's the same as what it was, and this is the residual entropy inequality. We define equilibrium to be when there is no flow and no temperature gradient. Now, that gives you this condition of equilibrium, and if you put all of this together, once again, we get the momentum balance equation, where we have this non-equilibrium term for the momentum exchange. If you assume it to be a linear function of velocity and a linear function of the temperature gradient, then we get, then we put that in there, we get this, and if you neglect the inertial term, you get an extended Darcy's law, where for the non-isothermal situations, we could potentially have flow as a result of temperature gradient. Now, whether it's significant or not, that's a different story. One can find out that this lambda KL is almost 0. Then you don't need to include it. But for non-isothermal, we could potentially have actually an extra term contributing to flow. I think, yeah, this is then a multi-component fluid. I'm going to stop here. Yes?
If we assume deformable solid skeleton, but non-deformable or rigid grains, it means that the only variable we need is the deformation tensor or the strain tensor. We don't need to have a rho s. Or
that is quite correct. For rigid grains,
means rho s is
then
constant.
rho s is
Constant, and
is constant.
and
So this cancels,
Yeah.
and then porosity is related to the
Yeah.
deformation. That is correct, and we don't need to include that. Very much. Other, yes?
I have a quick question. Maybe I don't fully understand you, but how do you solve your equation when you finally leave this the difference between your average term minus these microscopic terms? How do you finally solve this PTE? Because most of the measurements so far we are based on the average measurement. If finally you don't want to introduce any external assumptions to cancel these terms, finally you need to know almost everything also about your microscopic. So I'm not sure if I follow you, but
No, I think I understand what you are referring to. Oops. What is how do I go out of it? I used to know, but this is, okay. Yeah. Let me just make sure I understand your question. Oh no, it's the previous. It's the previous one here. Okay. Do you mean? Huh? Do you mean this term?
Yes. Yes.
So this is the average of the deviation of velocity.
Yes.
So in the development here, I put it next to the average of a stress tensor, and I call that the stress tensor. I don't have to do that. I can leave it like this, and I just either leave it like this, or for the sake of easy writing, I call this T prime. You call this T prime, you have del dot T prime. Then we go to our derivation here. I have that, oh yeah, that's because of the Skype I have at 2 o'clock. Okay, so if I go here, I think it's here. Yeah, when I write, for example, yeah. So now I have here, instead of t, I have that average t plus t prime. And this tells me that sum is equal to minus pressure. It doesn't, it never ever will appear by itself. Maybe there is another way to get information about it, but not from this. And then also to me, it's not important. If I find out that the stress tensor, that the average stress tensor plus that T prime is always equal to minus pressure, that's all I need, because then I go back to my momentum balance equation. Here I had average T plus T prime, the divergence of it, but I know that sum is equal to minus pressure gradient, so that's, I put that in there and I'm still done. I hope I answered the question. Otherwise I'll be happy to talk to you about it later. Okay? Yeah, any other questions? All right. Thank you. Yeah, and see you tomorrow morning.